Welcome back, mathematicians. Today we're reviewing 3.2, the derivative as a function. So last section we talked about the derivative of a function at a point, right? So we can write that as the derivative of a function f at a point. I think we used x naught. Right, and that gave us f prime of x naught equal to the limit as h goes to 0 of f of x naught plus h minus f of x naught divided by h. And this always gave us a number. So what if I make x naught the number, just x, the variable? Right, so that gives us the definition. So we say the derivative of the function f with respect to x, x, which is right, the variable, is the function f prime of x equal to the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Nothing too different from before, but finding x, we're not going to have like a number in there now. Let me write this a little nicer. Beautiful. Okay. All right, so let's do some vocab before we get into some examples. So if f prime of x exists, right, because it may not, because limits don't always exist. Oops. Then we say f is differentiable at x. Basically, differentiable kind of just means has a derivative. So then we can kind of go further and say if f prime of x exists, I kind of made a point. For if it's differentiable at x, it exists at a particular x, like 2 or something. Sorry about that. So if x exists for all x on the domain of f, then we say f is just differentiable. Differentiable, one of the hardest words for me as well. Okay, so the process of taking or finding the derivative is called differentiation. Alrighty, and so then what do we call this derivative? I've seen it as f of x prime, sorry, f prime of x. Well, if f of x equals y, we can also call this y prime. We also have this fun little thing. It's d over dx of f of x. This says take the derivative with respect to x. That's what that x is on the bottom. It could change. It could be like theta, it could be r. Okay, cool. So we can even have dy, dx, df of x. What else? There's a big D with a little subscript x of f of x. That's another way to do it. There's lots. So those are all the same thing, right? I just said they're all equal. Just different ways of writing the same thing. I usually like f prime or y prime more than dy over dx or df of dx. But sometimes you might have more than one variable. And that's when something like these two are important. Okay, so now let's do some examples. So we're going to find the derivative of 1 over x. We'll let that equal y. Let's let that equal f of x. Alrighty, so f prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x all over h. Right, so that looks like f of x plus h means every time there's an x in my function, I'm just going to put x plus h. So 1 over x plus h minus 1 over x all divided by h. I'm going to get a common denominator in the numerator, so we'll do like x over x times 1 over x plus h minus 1 over x times x plus h divided by x plus h. And this whole thing is divided by h. And instead of dividing everything by h, I'm actually going to multiply it by 1 over h. And that'll just make my life a little bit easier later on. So this is going to be x minus h, because that's negative goes to each term, over x plus h times 1 over h. Well, these two x's cancel out, x minus x, and we're left with the limit as h goes to 0 of negative h over x plus h times 1 over h. Perfect, and h cancels out. It's usually what we want. And we're left with the limit as h goes to 0, negative 1 x plus h. So now we have no problem plugging in h equal to 0, and I'll get negative 1 over x times x, which is just x squared. Perfect. So we can say that dx of 1 over x is equal to 1 over x squared. Perfect. Okay, let's do another one. So we're going to take the derivative of y equal to the square root of x with respect to x. Okay, so y prime is going to equal the limit as h goes to 0 of x plus h minus the square root of x all over h. So we learned a few sections ago how to counteract these type of problems, and we're going to multiply by the conjugate. Remember the conjugate, I just make this minus sign into a plus sign. Okay? We're going to FOIL the numerator. I'm actually going to keep the denominator the same. So that's going to be x plus h minus x over h times square root of x plus h plus square root of x. X minus x, those two cancel out. So we're left with h over h times the square root of x plus h plus the square root of x. Those two h's cancel out. That's always our dream, is for h's to cancel out. So left with 1 over square root of x plus h plus the square root of x. I have no problem plugging in h equals to 0. So I'll get 1 over the square root of x plus the square root of x, which is just the same as 1 over 2 square root of x. Alrighty. So basically, y prime is going to equal 1 over 2 square root of x. I want you guys to remember this derivative. It's very useful. Square root of x is derivative being 1 over 2 square root of x. Please remember this one. It'll come up a lot. We're going to learn some more things that'll make our life a little bit easier. But this, knowing the derivative of square root of x is just 1 over 2 root x, is going to make your life a lot easier. Okie dokie. So trying to think what else to show you guys. Okay. So in chapter 2, we said a function is a left or right continuous using left and right hand limits, right? So Sometimes we're not always going to have a limit of a derivative on a closed interval. And so we're going to have to do something similar. So chapter 2 we discussed. So similarly, don't know how to spell that word. We can say that f is differentiable on the closed interval AB if, so we're going to take h as it's going to 0 on the right hand side of f of a plus h minus f of a divided by h, which is the right hand derivative at a, and the limit as h goes to 0 from the left-hand side of f of b plus h minus f of b over h, which is the left-hand derivative, at b, exists. And f is also differential at every point in between. Okie dokie. So what if f isn't differentiable at every point in between? When can that happen? When does a derivative not exist? So let's look at f of x equal to the absolute value of x. So my handy dandy line tool, beautiful. So remember, we can write the absolute value of x as a piecewise function. It is x when x is greater than or equal to 0, and negative x when x is less than 0. Right? A negative number times a negative will give me a positive number, which is what I want. So I know that x and negative x, those are just lines. I know their slopes are, if we look at like y equals mx plus b, those slopes are going to be just the m, right? So in this case, there's like a hidden 1. And same here, there's like a negative 1 right there. So we know that each of those lines on their own is differentiable. What about at 0, where they intersect? So So let's look there. So let's find the, which one did I do first? Right-hand derivative. So we'll do, we'll call the RHD, right-hand derivative. So we'll take the limit as h goes to 0 positively. And that's going to be absolute value of x plus h minus the absolute value of x over h. And just kidding, it's not at x. So this is the right-hand derivative about 0. So let's make that a little bit more clear. Well, that just equals limit as h goes to 0 from the right-hand side, absolute value of h over h. So since h is approaching 0 from values that are greater than 0, those are positive values. So we can write the limit as h goes to 0 positively as h divided by h. Well, that's just the limit as h goes to 0 of 1, which equals 1, right? We can actually see that right here. If you remember y equals mx plus b, in this situation, b equals 0 and m either equals 1 or negative 1, depending on where x is. Alrighty, so then the left-hand derivative it's going to look pretty similar until I need to simplify absolute value of h. So now I'm coming from values that are smaller than h, smaller than 0. So absolute value of h I can write as negative h. So my slope here is 1. Whoopsies. And my slope here is negative 1. So the left-hand derivative doesn't equal the right-hand derivative. So no limit as h goes to 0 of f of 0 plus h minus f of 0 over h exists. So we can say like f prime of 0 does not exist. We call this a corner. You can kind of see it here too, right? It's like if you think in the corner of a room, I can't really walk on that. Usually I like to describe if like graphically you're looking at something and it's wondering if the derivative exists at that point. If I draw the tangent approaching that point and even at that point, if I can't walk on that, it doesn't exist. So I can't walk downhill and then immediately start walking up again. I need like a slow curve to get me there. So I can't walk over a corner. I'll like break my ankles or something. So now let's look at our second example, which is when f of x equals 1 over the square root of x. We already saw what this derivative is. But remember, this is only not 1 over square root of x. Crazy. Square root of x. Remember, this is already when x is greater than or equal to 0. So if we look at this graph, we're kind of looking something like that. So I know looking here that I don't see any problem areas other than probably right around, whoa, crazy, 0, right? So I can only find one side of the limit just because I can't exist on any negative numbers. So I can't approach 0 from numbers smaller, right? So I'm only going to have the right-hand derivative. So do the limit as h goes to 0 on the right-hand side, square root of 0 plus h minus the square root of 0 over h. Well, that equals the limit as h goes to 0 positively. Square root of h divided by h simplifies to one over the square root of h. And we know that as that goes to 0, my bottom number is getting really, really small. So 1 over a really small number is a really big number. We call that one infinity, right? If a limit equals infinity, we technically say the limit doesn't exist. It's unbounded. So if I draw some secant lines as I'm approaching 0, I see that they keep going and getting steeper and steeper. So f prime of 0 again does not exist. It exists everywhere else, just not there. So this one is kind of what we call a cusp. Another example of a cusp would be a graph that kind of looked like this. Very pointy. The point right there. So as I'm approaching this point, my derivative kind of turns into something pretty vertical. Like that. So more places derivatives don't exist. So the third example is called a vertical tangent. And that looks like if I have a graph going down like this, then boom, like that. Let me draw a better picture. This is still a function, but I kind of mostly have this vertical tangent. And that's not very cool. The next one is at a discontinuity. Right, so if I have a function going up, open circle here, and then say like a straight line right here. As I like try to test points to get here, right, the limit as like the difference is getting so small, it's not they're not matching up, because then this tangent over here is going this way, and these aren't matching. And what if we don't have a jump, we have a hole? Same thing. As H and H is getting smaller, the test points go this way. But then these points are going this way. And they're just like getting crazy and not going towards anything. Kind of looks like a fire. So this kind of gives us something about f of x if I know it about f prime of x. So basically we have this theorem, 3.2.1, and we say that differentiability implies continuity. The theorem says, whoa, we're zoomed in. Okay. If f is differentiable at x equals c, then f is continuous at x equals c. Note, continuity does not imply differentiability. So I can't say that if f is continuous, then it's differentiable, because we've shown that in corners and cusps. The function absolute value of x, that's continuous everywhere. It doesn't have a derivative at 0. All right, so that is it for 3.2, and I will see you guys in 3.3.